trigonometric functions. Okay, so we already have seen the extended definitions of the trigonometric functions in our previous video. We in fact also saw some elementary relationships among them and their values at some special angles, some special input values. Now today we are going to see their graphs. So this is how the topic starts up in this text. Graphs. And the authors write, when we draw the graphs of the trigonometric functions in the coordinate plane, we usually denote the independent variable, that is the input, by x instead of theta. Okay, so that means we will for example say sine x and not sine theta when we are specifically when we are talking about drawing their graphs. So now we are going to see their graphs. So first we will see the graph of the sine function. Now drawing the graph of sine function does not mean we are going to plot actual values, use actual values to plot actual points and then join them to get the graph. We are not going to do that, and it will be much like looking at the graph of this equation, for example, which we have already seen. We know that this equation represents the unit circle centered at the origin, a circle whose center lies at the origin and which has radius 1. So when we drew the circle, we of course did not plot actual points. We just drew the general shape of the circle as nicely as we can. So the same thing here also we are going to do. If you want to see the actual graphs, we will show to the best of our ability how the graph looks, but it's not the accurate thing. If you want to see the accurate thing, you can of course look in the text, or you can use this online application that you have, a site in fact which I mentioned before also. Desmos graphing calculator. If you search these terms, you will see that there is a site. If you go to that site, you supply the equation, it will give you the corresponding graph, and you can do many things there. You can zoom in, zoom out, draw multiple graphs in the same coordinate plane, many things you can do. Okay, so let us now see the graph. Desmos graphing calculator. It's very nice. I use it quite frequently. And not only just graphs of functions, you can draw graphs of equations like the things we saw previously. In fact, graphs of inequalities, it will give you the regions, everything it will do. So this is our x-axis and this is our y-axis, and we see here we are writing x because we are going to denote the independent variable by x. Otherwise, we would have written theta here, y. So on the x-axis, first of all, we are going to put some special angles so that we, those points where we know the value of sine function. And that will help us with the general structure of the graph. This is 0, so this is pi divided by 2. This is 2 pi divided by 2, that means pi. This is 3 pi by 2, 2 pi, 5 pi divided by 2, 3 pi, and so on. And on this side we have minus pi divided by 2, and here there is one point minus pi, and of course it goes on this side without any bound. Besides these x values, on the y-axis we need to locate 1 and minus 1, because we know that the sine function has its outputs lying between 1, minus 1 and 1. Geometrically, that corresponds to the fact that the graph of the sine function will lie in between these two horizontal lines. Let us first roughly draw the lines like this, dotted lines. Once we have the graph, we will get rid of them. Okay, now let me also locate the points on these horizontal lines where the graph will meet these lines. So things look like this. That is the rough shape of the graph. It is far from anything accurate. You can of course understand because I have just simply drawn it freehand. And it goes on either side without any bound. It continues. Okay. Let us now remove these lines. So this is the graph of the function pi equal to sine x. Domain and range already we know, but let's look at what they represent here geometrically. The domain is the entire set of real numbers, which the authors have decided to write in as an interval, and range is of course this closed interval minus 1, 1. Now what these things represent in the graph is that the domain is the entire set of real numbers, means for any x on the x-axis you have a corresponding y. For example, when your x is pi divided by 2, the y is 1. And for a given x, there of course is only one y because it's a function, a well-defined function. And the range being this set means that if you collect the images of the sine function, all the images, you put all the inputs which are all the real numbers and you collect all the images, then that set of images becomes this. So not only do all the outputs lie between -1 and 1, but in fact all real numbers lying between -1 and 1 appear as output. So there is no gap. All the values between -1 and 1 are taken, and in fact multiple times, again and again after regular intervals. That of course is periodicity of sine function, to which we are coming later. Okay, so this is the rough shape of the graph. I should not say the graph of the sine function, but the rough shape of the graph of the sine function, ordinary sine function. Next we see the graph of cosine. The cosine graph is, in terms of shape, just the sine graph, but it is shifted slightly. You shift the sine graph horizontally by a definite amount in a definite direction, you get the cosine graph. And these geometric properties of course correspond to similar things equation wise. Okay, so first of all let us identically put those points. So again 0, pi divided by 2, pi, 3 pi divided by 2, 2 pi, 5 pi by 2, 3 pi, and so on. And on this side minus pi divided by 2, minus pi, and so on. On the y-axis again we locate -1 and 1. This is 1. Okay, since we already saw those lines, we are not going to do that again. Instead, let's just directly guess the lowest points. Pi, then 3 pi, 2 pi, and it will go like that. So on this side, minus pi by 2 minus pi, and on the positive side of the y-axis okay. Already this doesn't look good. then it goes like that. So you can see that this graph looks just like this graph. This is the graph of the cosine function, but this is just this graph shifted to the left by a length pi divided by 2. This one is looking pointy. There is no sharp corner or anything like that. It is smooth throughout, if that makes sense. So this is the graph of y equal to cos x. In this case also we have the same domain, of course. The entire set of real numbers and the same range, this closed interval of length 2. But the functions, of course, are entirely different functions. So that is cos x. Here also the value, all the outputs lie between -1 and 1, and in fact more precisely this is the range. Next we look at the graph of tan x. Now if you, so we have not plotted points and we are just simply stating a fact which you may believe or you may not believe, unless you yourself, of course, use a graphing, either you use a graphing calculator or you actually plot the points and see that the graph is like this. But without doing any of these two things, you can in fact know a lot of information about this, the general shape of the graph, just from the definitions of sine and cosine, which however we are not going to do here, but we are going to do that for the tangent function. We will see that without actually plotting the points, using just the definition of tangent, or in fact its relationship to sine and cosine, we will be able to say many things about why its graph looks like how it looks. Okay, so let us see next the graph of the tangent function. Like before, we identify those points. And so on. Now you know from the definition of tan x or tan theta, that it is not defined at those points where cos theta becomes 0. That is because of this relationship. And you can see from this graph where cos theta is 0, or because we are not using theta, so to avoid unnecessary confusion, let us write x. Cos x becomes 0 at these points. At these points the y values are all 0. That means integer multiples of pi by 2, and that too not just any integer multiples, odd integer multiples of pi by 2. That is, these values of x make cos x 0, where n is any integer, and these values of x we have to avoid here. So at those points the tangent function will have no value. Correspondingly, there will be no point on the graph of the tangent function at those input values, and that again translates into this. If you draw these vertical lines through those problematic inputs, which in fact will not be inputs, then the graph of the tangent function will not touch these lines. So let's now first of all see the graph and then try to see why the graph looks the way it does, just from this relation and how sin x and cos x behave. So the graph, unlike those two previous graphs, is not in one piece. It is a collection of infinitely many disconnected pieces, and all the pieces look identical, and they look like this. It will not touch this line. It will get closer and closer to this line without ever touching it. The vertical lines, of course, are not parts of the graph. These curves are. Okay, so that here the graph is a disconnected, it's not in one piece. Now let us see. So you can see a couple of things before we go to that thing. That is why the graph has this particular shape. You can see a number of things. First of all, the graphs look identical on these portions, these vertical strips. These parts look identical. And the other thing is that any part, if you look at it, it neither touches this line nor touches this line. Do you just simply see why? Because if it touched this line, for example, say if it was like this, then definitely the tangent would have a value at pi divided by 2, a finite y value, which however is not possible, because at pi divided by 2 radian, cosine of that becomes 0. So that's why this does not touch the line, never. It gets closer and closer to the line as your input gets closer and closer to pi by 2. So let's now try to see from the definition of tan x, or simply from this relationship itself, that why this behavior. So we are going to go back to the definition of these functions, which involves that unit circle. which is not a circle in fact, but you have to understand that it's a circle. It is something that is approximately a circle. Strictly speaking, it is just something, a closed curve, which here I don't know why I always mess up. Anyway, okay, so let us now concentrate on this interval, the x values lying between minus pi by 2 and pi by 2 in this manner. Minus pi by 2 is strictly less than x is strictly less than pi divided by 2. Since we are not allowed to take these values themselves, minus pi by 2 and pi by 2, so that's why we are considering strict inequalities and not things like this. Okay, now when x lies in this interval, what does that correspond to here? I mean, x is the radian measure of an angle, right? Now what we have learned in the previous video when we defined these functions is that first of all you need to imagine the angle in its standard position, that is the vertex of the angle should lie at the origin and the initial line of the angle should coincide with the positive x-axis, and then based on what the terminal line is, then you then have the trigonometric functions. Okay, so let's now first of all look at the positive values of x. A positive x, for example, corresponds to an angle whose terminal side is this, terminal ray is this. So this is our angle, this is the initial ray, and this is the terminal ray. So the rotation is anticlockwise or counterclockwise, so it is positive, right? So now what is said, this is x1. Okay, so this much is x1 radian, and that x1 radian corresponds to this point whose coordinates are say alpha 1 comma beta 1, or for the sake of simplicity let us take u1 and v1. So this is u1 and this is v1, and by the definition of tan x, or rather tan x1, say tan x1 is v1 divided by u1. Fine, that is just simply the definition. Okay, now what will happen if x1 increases, if the angle is larger? Say it is this x2, then this is your new point u2 comma v2. Note that u1 is greater than u2, but v2 is greater than v1. You can clearly see that from the figure. Tan x2 is equal to v2 divided by u2. Now, in fact, if you actually find the values, you will see that despite this contrasting trend, 1 is increasing, the y is increasing and the x is decreasing, the quotient in fact increases, and that is why on the positive side of the x-axis, I mean x1 lies here, no, as a real number x1 lies here, x2 lies here, after x1 it appears. So there the value is more, and it gets more and more. Okay. Now the thing is that as this terminal line approaches the y-axis without of course coinciding with it, it cannot coincide with the y-axis, because if you are considering this angle, then you are considering pi divided by 2, at which point tan x is not defined. So if your terminal line is very close to the positive x-axis in this sense, then your y is in fact still greater than all the previous y's, and your x coordinate however is shrinking, it is decreasing, the y coordinate is increasing. What do you think will ultimately happen? Tan x is, or because we are denoting the things here by u and v, this, what will happen to this quotient? Note that as our terminal ray goes like this, v increases, fine, v is increasing, but there is a limit to this increase, there is a bound. No matter how large v becomes, this is the maximum v that you can have, because this length is 1. All the other lengths that you see of the perpendiculars, they are all less than 1. So v is always less than 1. No matter how close to 1 it is always less than 1. Correspondingly, u is decreasing. This is your first u1, then u2, then u3, u4. It is decreasing and it's getting closer and closer to 0, and it's in the numerator, it's in the denominator. So it is making the ratio, it's making the quotient increase. However, unlike the increase of u in this bounded manner, the decrease of u is unbounded. You can become as close, you can make u as close to 0 as possible, and that is why the corresponding increase in the total quotient brought about by this decrease of u cannot be controlled by this v itself being very large, because it actually cannot be very large. It can be very close to 1, but quickly this decrease of u and the corresponding increase of 1 over u will overwhelm this thing. So it will not, when you are very close to this region, this practically has no effect on this whole thing. So having a v in the numerator is actually as good as having just 1. You cannot have 1 here, but I am just simply saying. So 1 over u increases without any bound, and that is why when your x reaches pi by 2 from this side, your quotient, which is in fact tan x, increases without any bound. That's why the graph on this side looks like this, and the exact thing happens on the negative side of the x-axis, on this side. And what does that correspond to here? Negative values of x, which correspond to negative radian measures of angles, which are, if you put them in their standard position, angles which look like this, whose terminal rays lie below this x-axis. So the rotation is clockwise. That is why that negativity. Now here also you can see that as your terminal ray approaches the negative y-axis, numerically the same thing will happen, but in terms of sign you will have a minus sign. And why is that minus sign? Because you see here, for example, here also you have some x coordinate, y coordinate. So that say this is u prime, v prime. u prime is still positive because everything is happening on this side, but v prime is negative. So all the tan values for these negative values of x or tan x themselves are negative. So that same behavior of numerically becoming larger and larger without any bound now comes with a negative sign. So that's why the behavior on this side is this. It goes down, it plummets without any bound, without ever reaching or touching this line, of course. And these points are the points where, of course, the function becomes meaningless, the function is not defined, and those are the points where things have broken. They are points of discontinuity. And once you go beyond these points, the same behavior is repeated infinitely many times. Okay, so the graph of tan x is a collection of these broken individual graphs, and they are all identical, and the things happen after regular intervals. Same thing again and again. Now here, unlike the sine and cosine graph, you can clearly see from the graph also and from the little analysis that we have done here, tan x is not a bounded function. Okay, its values are not lying between, say, two horizontal lines or anything like that. And in fact, the range in this case is the entire set of real numbers, because all real numbers appear as outputs multiple times, infinitely many times in fact. Domain, however, from the set of real numbers, you have to remove these problematic points, which you already know what they are. They are the odd integer multiples of pi divided by 2, the points precisely where cos x becomes 0. So how have the authors written it? In terms of words, I think you can write in whatever way you want to write, but the authors have written like this: all real numbers except the odd integer multiples of pi divided by 2. So that is tan x. Now I need to write that. This same thing you can do with the sin x and cos x graphs also, to at least say some things qualitatively about the graph. Next we'll look at the graph of what is given here, secant x. Secant x graph, that function also has problematic points or singularities where things go wrong. And in fact, what is the relationship between secant x and cos x? Secant x is 1 divided by cos x. So the problem that you have with tan x, that same problem you have with secant x, that precisely those same points where cos x becomes 0 have to be removed from the domain. So actually these points themselves. And just like the tangent function, the secant function also is not bounded. Okay, so our points are 0, pi divided by 2, pi, 3 pi divided by 2, 2 pi, and so on this side. And we draw those corresponding lines which have to be avoided by the graph. But here, however, we will again need to locate -1 and 1 for a different type of reason. The graph of secant x is also broken like that of tan x, and the individual portions look like this. On that side again you have like this, these things alternate. This is 1 and this is -1. So unlike the graphs of sine and cos, which are trapped between these two horizontal lines, the graph of secant x, however, it cannot, in fact, it does not lie in that region at all. It lies outside of that region formed by those two horizontal lines, y equal to 1 and y equal to -1, and the individual portions look like this. And that is why here domain, of course, is just like tan x. We have avoided these points, the odd integer multiples of pi divided by 2. Both positive and negative. Plus or minus 5 pi by 2, 7 pi by 2, and so on. So those points have to be avoided. X can be any real number except these. Now range is all the real numbers between -infinity and 1, and all the real numbers between 1 and +infinity. and these points -1 and 1 are actually, these values are taken on as output. Okay, so that is the graph of secant x. Next we see the graph of cosecant x, which is almost like this, I mean shape wise, but the position is I mean you shift this graph and you get this graph. At least the general shape you get. Wait, but here the problematic points, however, because we are going to draw the graph of cosecant x, so which is 1 over sin x, so we need to avoid those points where sin x becomes 0. That means all multiples of pi. Okay. So the points we have to avoid are these now, and hence we have to draw vertical lines passing through them. Again, -1 and 1 have to be located. Okay, now here these if you want, you can call this union and this intersection. The union, the first union on this side of the x-axis appears here. Sine pi by 2 is 1, so cosecant pi by 2 is its reciprocal, which is also 1. Yes. And the intersections, the mountains appear here. One will appear here, its peak will be there, and the other one will have its peak here. So that means y is equal to cosecant x. This is 1 this is minus 1. And what about the domain? Domain here will change because we have avoided all the integer multiples of pi. That means here x can be any real number other than these 0 plus or minus pi plus or minus 2 pi, etc. And what about range? Range is again this thing, this or this one, that is this, and union this. One more is left, the graph of the cotangent function. You see, recall that the graph of the tan function was like this. Now, for cotangent it will be like this. X cotangent function. Cot x is cos x divided by sin x. So here, although the function is like a sort of mirror image of the graph of the tan function, but the lines that have to be avoided, that here however will be just like these lines, because here we had to avoid the points where sin x becomes 0. The same thing we have to do here, because this is 1 over sin x, so sin x should not be 0, and cot x is cos x divided by sin x. So here also sin x should not be 0. So that means we have to avoid these lines again. Okay, and the graph will now look like this. At pi divided by 2, it will become 0 this time. Okay. Note that in case of the tangent function, these points were avoided. Pi divided by 2, 3 pi by 2, but Now they belong to the domain of cotangent, and in fact the cotangent function is 0 at these points. Freehand drawing is awful. My freehand drawing, that is. And just like that, there is another one like this. This pattern continues without any end on either side. So this is y equal to cot x. Domain is the same like before. Oh, what the x have to not be equal to these things. The range, however, just like tan x, is now the entire set of real numbers, because tan x gives us all the real numbers, so its reciprocal also will give us all the real numbers. So these are the graphs of the 6 basic trigonometric functions with x as a radian measure of some angle. Now each function's periodicity, that is this pattern, or the fact that its values repeat after regular intervals, which one can see clearly from these graphs. And now next we come to the periodicity of these functions. These functions, of course, are not just some mathematical curiosity. Right from their very beginning, when they are introduced for the first time, when their definition involves only a right angle triangle, there itself you see that they are highly applicable. And now our extended definition will also be shown to be applicable in this text, highly applicable. In fact, okay, we will come to that thing, but let us first see periodicity of these functions, the quality of being periodic, that is the ability of these functions to take on the same values again and again in a regular manner, not in a haphazard chaotic manner. When an angle of measure x and an angle of measure x plus 2 pi radian are put in their standard position, then their terminal rays of course coincide, because whatever x is, say x is this much, x plus 2 pi will then be like this, 2 pi plus x. So the terminal rays coincide when you put the angles in their standard position. When an angle of measure x radian and an angle of measure x plus 2 pi radian are in standard position, their terminal rays coincide, and that is why the values of the trigonometric functions at these two points will be exactly the same, because the terminal ray is the same. So the point at which the terminal ray will intersect that unit circle, the coordinates of that point will in fact determine the values of the trigonometric function, no, by our definition. So that is why those functions will have the same values at x and x plus 2 pi. The two angles therefore have the same trigonometric values. Angles having the same trigonometric values means angles having the same values for all the trigonometric functions. For example, cosine x plus 2 pi by our definition of cosine x will be equal to cosine x, simply because the terminal rays of these two angles are in fact the same ray. Equal to cos x. Functions like the trigonometric functions whose values repeat at regular intervals are called periodic. And in fact, here is the more precise definition. And that definition is this: a function f of x is called periodic if there is a positive real number p such that I think I need ink again. such that f of x plus p is equal to f of x for all x, for all x in the domain of f, of course, that thing is understood, and the smallest such number p for which this thing happens is called the period of f of x. So as we can see, in the graphs of the trigonometric functions, tangent and cotangent functions have period pi, and the remaining four functions have period 2 pi. This I need you to see. Okay, I need you to verify. Just go to the graphs of these functions and match everything with the definition. You will see that pi is in fact the smallest positive real number for which tan x plus pi is equal to tan x, or in fact pi is the smallest length of an interval on the positive side of the x-axis, where the entire behavior of tan x is captured. After pi, that behavior will again be repeated. Okay, and it will keep on repeating after that. For the other functions, for cot x also that is pi, and for the other functions it is 2 pi. And there is in fact a small table also which summarizes these things about the periods of these functions. Trigonometric functions. How is it written? Period pi. So, okay, so they have categorized according to the period. They have categorized the functions. Tan x plus pi is equal to tan x, cot x plus pi is equal to cot x, and you have to understand that these equations are also coming with those restrictions on x. That is, you have to see that the left and the right hand sides make sense. That is, you should not put those values of x which will make this cotangent undefined. then those functions with period 2 pi. Sine x, cos x, secant x. Oh, okay, I have written cos x already. I've said cos of this. Okay, so that's how the periodic nature of all these functions look. Now, one can in fact create other trigonometric functions by tweaking the input and thereby changing the period actually. What we mean by that is next shown by these two things, these two examples. Again, we are going to look at graphs. This is going to be slightly more complicated than our original graphs of the trigonometric functions because two graphs are going to be now drawn at once. And on this side we have 1, 2, 3, 4. Okay, I am barely able to draw all the things that are shown in this figure. Anyway, okay, so let me now carefully first of all put the points 1, 2, 3, 4. This is pi. Okay. Two pi. 3 pi. 4 pi. This is minus pi, this point. Okay, now next comes So that means yes. Okay, it's going to look extremely bad, but you just take that fact away from this, that the graph just passes through these points. Okay, you just don't consider the exact shape of this. It's a sine graph, you just consider that fact. But it's not just simply sine x, because that can't be. No, sine x of course passes through x equal to 0, I mean passes through the origin. That thing has not happened. Or is it the cosine? Okay, it is cosine, it's not sine. But still it's not actually the graph of cos x, because cos pi radians we know is -1, which we don't see here. Had this been the graph of cos x, we should have had a portion like this. It is, however, the graph of cos 2x. Now here, if one then on top of it draws the graph of original cos x, what would that then look like? That will obviously look like this. The somewhat spread out graph is the graph of actual cosine function without any modification done to the input. There the input has been modified. We are not taking the actual input but twice its value. The fact that we have taken twice its value has shrunk the period from 2 pi to pi. Do you see why? Because now the things will be repeated, the input values are repeated twice more frequently. So that's why everything will happen at half the distance. So that is why the period of cos 2x is pi and not 2 pi. I have the graph here, you can see. The red one is the cos x and the blue one is cos 2x. That's what I have tried to draw here in a rather messy manner, from which you can just simply make out the period and that's just it. It looks awful. So this one is shorter period function cos 2x, whose period is pi, and there is a longer one also which I am not going to draw, although it won't be this messy because if you want to call it, the frequency is more. Here the frequency is less. If you take half of the input, in place of x there we consider 2x. Here if you consider x divided by 2, then the graph will be even more spread out. Its wavelength will increase but frequency will, and hence correspondingly frequency will decrease. The frequency of these repetitions will decrease. So this will have period not 2 pi but larger. Cos x by 2 will have period 4 pi. So that will be the shorter period, which I am not drawing. Okay, you can see that here, and it's also of course there in the text. Now we come to the question of why periodic functions are so important. So then the authors write the importance of the periodic functions stems from the fact that many things that we see around us are periodic in nature. Many actual physical, chemical, or even biological phenomena are periodic. Much of the behavior we study in science are periodic, and a list of things have been given. Brain waves and heartbeats are periodic, of course. As are household voltage and electric current. In fact, most of the things that we see around us are in fact periodic. The electromagnetic field that heats food in a microwave oven is periodic. Are periodic. Then of course cash flow in seasonal businesses and behavior of rotational machinery, these are all periodic. Seasonal businesses don't do good business throughout the year. Only in their peak season the cash comes in more because there is more business. Maybe it's tourism or something else. So seasonal businesses and the cash flow in seasonal businesses and the behavior of in fact, you can say that seasonal businesses themselves are periodic in the sense that they do not run the business throughout the year, only in some seasons they open and then again they close down. And the behavior of rotational machinery. The seasons themselves are I don't like, okay, I am not in a mood to write down all these things, okay. I should have in fact said it, should have read it instead. Seasons themselves are of course periodic, hence you have this summer, winter and everything. All the things have been quite messed up now, but still, and so is the weather. The phases of the moon are periodic, as are the motions of the planets. And in fact, there is strong evidence that the ice ages are periodic with a period of about 90,000 to 100,000 years. And in fact, the atoms and molecules, they are vibrating. Even in a solid, atoms are never at rest. There is a minimum amount of vibration. Those things are also periodic. In fact, based on atomic vibrations, we have atomic clocks, which are extremely accurate. Now the question is, if so many things are periodic, then why are we not studying periodic functions in general, and why are we considering only on trigonometric functions? That is because there is a theorem in advanced calculus which says that if a periodic function is a somewhat well-behaved function in a very well-defined sense, and in fact is the kind of function that we are interested in all these applications, then such a function can be expressed as an algebraic combination of sines and cosines, something like this. Okay, so once you know the calculus of sines and cosines, you practically know everything about this type of periodic functions, which are not necessarily the trigonometric functions. Particularly these examples that the authors have given slowly lead us to something called Fourier series, which are theories that arise as solutions to differential equations, and those differential equations are related to phenomena that we have in real life, actual engineering and physical phenomena. So we will see in the next calculus video the evenness and oddness of these functions, where in fact this section ends, and then we will start solving the exercises. So that's just it for tonight. If you want to make a remark or you want to write some comment, you can use the comment section below, or you can mail me at my usual address. The link will be there in the description. Tomorrow we again have Gallian's exercises, and this coming Sunday again we have mathematical analysis. So with that, this is all for tonight. So see you tomorrow with Gallian's exercises. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.